In this course, we have looked so far at different approximation methods in quantum mechanics. All our methods so far, however, was focused on the case where the Hamiltonian was time independent. We have done perturbation theory before, but that was also for time independent Hamiltonians. We are going to change gears now and take a look at time dependent perturbation theory. Of course, this is very important in understanding the way quantum mechanical systems evolve in time. The basic equation of time evolution in quantum mechanics is, as you all know, the time-dependent Schrodinger equation. What we really should be calling the Schrodinger equation. IH cross del del t of the ket psi is equal to the Hamiltonian operator H acting on the ket psi. Now, in time-dependent perturbation theory, the basic setup that we use is as follows. We think of the H, the Hamiltonian, as a sum of two pieces, H0 plus V of t, where H0 is a time-independent exactly solved Hamiltonian with a given spectrum. The spectrum is, of course, the eigenvalues and eigenkets of H0. We assume that we know completely this particular spectrum. We know all the phi n's such that H0 acting on phi n are equal to epsilon n phi n. The phi n's, these eigenkets, are orthonormal, so the bra phi n ket phi m overlap is delta mn. They also form a complete set. So the ket phi n, bra phi n operator is the identity operator when you sum it up over all n. All this should be very familiar to you. We have already covered this in some detail when we talked about time-independent perturbation theory. The difference is in the perturbation. Here we are assuming that the perturbation V of t is a function of t. But as always, we are going to assume that it is, in some sense, small compared to H0. Exactly what we mean when we say small is something that will be clear in the course of the next few lectures. The question here is, how does the time evolution of the state ket psi of t change because of the effect of this perturbation V of t? Now, obviously, a general ket can be expanded in the eigenbasis of H0, simply because the eigenbasis of H0 is assumed to be a complete set. So ket psi of t can be written down as a sum over all the states n, ant ket phi n, where ant are the time-dependent coefficients which tell us about the time evolution of the ket psi of t. Now, what we need to do now is plug this form of psi of t into the Schrodinger equation IH cross del psi del t equals H psi. Now on the left hand side, IH cross del psi del t will of course become IH cross sum over all n an dot t phi n. Remember, the ket phi n's are eigenkets of the Hamiltonian H0, which is assumed to be time independent. So ket phi n are independent of time. And therefore the derivative only acts on the coefficients an of t. On the right hand side, we have H0 plus V acting on the state, and since H0 and V are both linear operators, they will go inside the sum and cross the A and D coefficients, hitting directly the ket phi n. H0 acting on ket phi n will give rise to the first term, which is epsilon n phi n, since epsilon n is the eigenvalue corresponding to the eigenket phi n of H0. V of t acting on phi n gives us some state which we cannot really specify any further at this stage. The next step would be to convert this set of equations involving vectors into equations involving complex numbers. To do this, what we do is hit both sides of the equation with the bra phi m, where m is some other label, or maybe m could also be n, of course. Now, when I do that, the fact that phi m and phi n are orthonormal immediately gives us the statement that on the left hand side we have IH cross sum over n, an dot t delta mn. The sum over n now becomes trivial and gives us IH cross am dot of t, which is what you have on the left hand side. On the right hand side, the first term again gives rise to a delta mn and the sum simplifies to epsilon m am of t. The final term will of course not simplify any further, at least the sum will still remain. You will get sum over n an of t times the matrix element bra phi m v of t ket phi n. So this is what we call the matrix element Vmn. And the only difference between our earlier uses of this quantity in perturbation theory and this one is that here Vmn can explicitly depend on time. Now we can rewrite this equation by simply dividing by IH cross and moving the first term on the right to the left, and this gives us an expression like this. If you look carefully at the term on the left, it is crying out for an integrating factor, e to the power I by h cross epsilon mt. And if you multiply through both sides of the equation by that, the left hand side becomes a total time derivative d dt of am e to the power I by h cross epsilon mt. Now, this suggests that what we can do is change our variables am to a new set of variables. The coefficients am change to the coefficient cn, or in general an changes to cn, where cn is given by an e to the power I by h cross epsilon n times t. So if I do that, the right hand side obviously becomes cm dot, whereas the right hand side has to be changed a bit. The ant on the right has to be changed to cnt e to the power minus I by h cross epsilon n t, and now I can easily move the exponential of I by h cross epsilon mt sitting on the left of this expression into the sum. The sum, remember, depends only on n, and so e to the power I by h cross epsilon mt can move into the sum without any problem. And this leads to the following expression. The e to the power I by h cross epsilon mt and e to the power I by h cross minus epsilon nt can be combined together into a single exponential factor. And what we will do now is combine the matrix element Vmn of t and this phase factor e to the power I by h cross epsilon m minus epsilon n into t into a quantity which we will call V tilde mn of t. And this leads us to a slightly less cumbersome form of this set of equations. These now give us the coupled differential equations Cm dot t equal to minus I by h cross sum over all n V tilde mn of t Cnt. Note that we have one equation for each coefficient that we have. And let's repeat once again, V tilde mnt is simply this quantity, and very often this quantity epsilon m minus epsilon n by h cross is replaced by a suggestive shortcut omega mn. Omega mn is of course the frequency of radiation that would be released if a system transits from a state with energy epsilon m to a state with energy epsilon n. Right now, of course, we are not talking about any such thing as photons or anything. What all we are saying is this is a abbreviation that we are going to use. And so V tilde mn t is e to the power I omega mn t V mn t with omega mn epsilon m minus epsilon n by h bar. Now this is a set of coupled differential equations, because in each equation for a particular m, all Cn's are actually present on the right hand side. Now one thing that we can do is change this by integrating, and integration from some time t0 to a time t immediately gives us this expression. The left hand side becomes Cm of at t minus Cm at t0, whereas the right hand side is replaced by an integral. It's the integral from my t0 to t of minus I by h cross sum over n of v tilde mn t prime Cn t prime dt prime. So now while this looks like an expression for Cm of t, this really is not a solution to our original coupled differential equations, because the unknown quantities, the coefficients at the time t, are sitting both on the left and on the right of this equation. So these are still equations. The only difference is that we have changed coupled differential equations to a bunch of coupled integral equations. Now coupled differential equations, infinitely many of them, were hard enough, but we seem to have made things even worse for ourselves. Coupled integral equations are things which we have not even looked at perhaps earlier. Indeed, even simple integral equations are not really everyday stuff for most physics students. So how do we claim that this is actually something that helps? Well, note that when we write the equations in this form, this is an equation which has a Cnt prime on the right hand side, but this equation works not only for m but works for every value of index. In particular, it works for Cnt prime. So what we can do is we can actually replace the Cnt prime on the right hand side of this equation by what this equation itself says. In other words, what we can do is write Cmt is equal to Cmt0 minus I by h cross sum over n integral from t0 to t v tilde mn t prime. So far, this was all that we had earlier, and now what we have done is we have replaced the Cnt prime by the thing in red in the brackets. Cnt prime is given by Cnt0 minus I by h cross sum over a different index n prime. You can no longer use the dummy index of summation to be n, because I am talking about a specific n here. t0 to t v tilde nn prime at t double prime Cn prime at t double prime dt double prime. So just like we had to change the summation index from n to n prime, we also have to change the dummy index of integration from t prime to t double prime, because t prime is a specific time here, the upper limit of the integral. And then we of course integrate this whole thing with respect to t prime. So apart from making this look even more complicated than it was, what advantage does this give us? Well, we can simply break this up into pieces. The first piece is of course Cmt0, which we already had. The next piece becomes an integral minus I by h cross sum over n t0 to t v tilde mn t prime dt prime multiplied by Cnt0. Note that Cnt0 is independent of time and it is actually a known quantity. Because you know the state at time t0, you should know all the coefficients at time t0. So where have the unknown quantities gone? The unknown quantities have now taken refuge in the third term. Plus minus I by h cross whole square, sum over both n and n prime, a double sum, and now you have a double integral from t0 to t, that's t prime running from t0 to t, then t double prime running from t0 to t prime, of the product v tilde mn t prime v tilde nn prime t double prime multiplied by Cn prime T double prime. So this is where the unknown quantities are now. Now let me point out that our basic presumption is that the potential V is a small quantity. So V of t is going to be small, and the more V tildes you have in an expression, the smaller it is going to be. So as you can see, what we have managed to do is push the unknown quantity. The value of these coefficients at time t0 are already known, but those at other times are things that we are trying to find out. We have pushed that unknown quantity into a second order term which has two V tildes. As a result, it's a small term which we might even ignore. In fact, we don't have to stop here. What we can definitely do is replace Cn prime T double prime by using our original equation, and that will of course give me Cn prime T0 plus another term which involves one more V tilde. I'm not going to bother to write this down explicitly. All I'm going to do is show you this one piece Cn T0, which now converts this term entirely into a thing which we can calculate based on just the matrix elements of the potential. No need to know the unknown quantities Cn of t for this. The unknown quantity has been pushed to the next term, and of course we can keep on doing this over and over again and push the unknown quantities deeper and deeper into this perturbation sum. This is a perturbation sum because each term has a fixed number of V tildes, so we are effectively expanding in powers of V tilde. And as we have done before in time independent perturbation theory, large number of potential terms means a small contribution. So hopefully the first few terms are going to give me good enough results. Indeed, in the rest of this course, we are not even going to bother about higher order terms here. We are going to primarily focus on first order time dependent perturbation theory. What that means, of course, is we are going to ignore all terms on the right hand side above where there are more than one V tildes. So the first order approximation simply becomes Cm at t is Cm t0 minus I by h cross sum over all n t0 to t V tilde mn t prime dt prime times Cn at t0. Let me stress once again, the coefficients are all known at time t0, at least that's our premise. So there should be no difficulty in calculating this sum whatsoever. This then is the basic equation which tells us how the coefficients of the state in terms of the unperturbed basis vectors evolve in time, at least according to first order time dependent perturbation theory. Now a special situation simplifies this expression considerably, and this special situation also happens to be a pretty useful one. This is when the initial state is one of the energy eigenstates of the unperturbed Hamiltonian. So, if we start with the state ket phi I, then Cn t0 must be 1 when n is equal to I and must be 0 whenever n is not equal to I. That means Cn at t0 must be equal to delta ni, where delta is the Kronecker delta symbol. The presence of the Kronecker delta symbol in the sum over n simplifies the sum considerably. All terms vanish except for the term where n is equal to I. So you are left with Cnt is now equal to delta ni minus I by h cross. The sum has gone away. You are just left with integral from t0 to t V tilde nit prime tt prime. Okay, let us hope that there will be no confusion between the I index, which stands for the initial state, and square root of minus 1, the I sits along with the h bar in the minus I by h bar factor. Now that we have derived the basic equation of first order time dependent perturbation theory, let us put it to use. The first application that we will deal with is a rather simple one. Here we are going to consider a perturbation which lasts only for a finite amount of time. And that means that in the remote past, the Hamiltonian of the system was H0, the unperturbed Hamiltonian. Not only that, in the remote future or in some time after the perturbation is over, the Hamiltonian is again going to be H0. Let us now ask the question that if the system was found in an eigenstate of the unperturbed Hamiltonian phi I initially, that is before the perturbation started, what is the probability that it will be found in a different energy eigenstate phi k after the perturbation is over? Here phi k is an eigenstate of H0 again. Now this probability is given by the coefficient ak mod squared at some time t after the perturbation has gone away. Note that ak and ck, our coefficients that we have written down the equation for, only differs in a time dependent phase factor. So their modular squares are exactly the same. So the answer to this question is given by ck mod square, and since k is not equal to I, delta ni vanishes. So you just take the mod square of the rest of the terms and you are left with the probability that the system goes from I to k is given by 1 by h cross square modular square of this integral from minus infinity to plus infinity of v tilde kit dt, or just replacing v tilde kit by its expression v kit e to the I omega kit. Of course, here the integral is really being done from the initial time when the system is in the state phi I to the final time where the observation is being made. But since the perturbation vkit is non-zero only over a finite period of time, you can easily extend this integral from minus infinity to plus infinity. No extra contribution is going to come from this additional interval that you have added because vkit is 0 there anyway. So this is our expression for the probability that we required. Let us now turn to a slightly more non-trivial application. Here we consider a perturbation which is 0 in the distant past and then changes over a finite period of time and finally reaches a steady value which we are going to call V infinity. So the previous example was a case where V infinity was in fact 0. But here we are considering a possibility of a non-zero V infinity. That is, the perturbation has actually caused the Hamiltonian to change over time. So here, initially you had a time independent Hamiltonian H0. After a long time, the Hamiltonian is again time independent, but it is really not the original one any longer. It is H0 plus V of infinity. So we start with an assumption that the system is in the state phi I in the distant past. Say T0 has been pushed back to minus infinity, and phi I, as always, is an energy eigenkette of our unperturbed Hamiltonian, or rather the initial Hamiltonian. To calculate Ci, we need to just plug in our formula, and what we get is Ci at time t is given by 1 minus I by h cross minus infinity to t Vii t prime dt prime. Though the integral actually stretches all the way from minus infinity to time t, you should realize that the contribution really starts only after the perturbation becomes non-zero. So maybe at some finite time t equal to 0, let's say. And as long as the perturbation has died out and we are looking at the system long time after the perturbation has reached a steady value, what we can do is we can replace this integral by a very simple expression. We can replace the Vit prime in the integrand for the major part by its final value, which is Vii infinity, and For all practical purposes, we can approximate Ci perfectly well by this expression, 1 minus I by h cross Vii infinity times the time t. So all we are really doing here is we are ignoring the contribution to this integral of the small time between 0 to some value after which the potential has become steady. If small t is large enough, that is, if we are looking far enough into the future, this approximation is perfectly valid. Now what about transition to other states? This, of course, is the probability amplitude that the system will stay in the same state as the initial one. The probability that it will transit into another state, k not equal to I, is given by this amplitude ck, which is minus I by h cross integral from minus infinity to t vki t prime e to the I omega ki t prime dt prime. And here, of course, the delta ki term is simply 0 because k is not equal to I. In the next step, we carry out an integration by parts. Note that e to the I omega ki t prime is a function which we can integrate very easily, and we use that to write ck in the following form. You have an integrated out part which is vki t prime e to the I omega ki t prime by I omega ki times the I by h cross that you had. That gives you the first term here, and you have a second term which of course comes from differentiation of vki t prime with respect to t prime and the integral of the second function as is standard in an integration by parts formula. Note that in the lower limit minus infinity, the value of vki t prime is actually 0. So the integrated out part only has contributions from the upper limit t, and we are assuming once again that t is a time which is after the potential perturbation has steadied out. So vki at t is the same as vki at infinity. So this is the form which ck takes. Now that we have found expressions for all the coefficients cn at time t, we are in a position to reconstruct the state of the system at time t. Remember, we are talking about a situation where the system was in the state phi I, an eigenstate of the unperturbed Hamiltonian in the remote past, and we are trying to figure out what is the state at some time t after the perturbation has steadied out. So just to recount, Ci of t is given by this approximate expression, 1 minus I by h cross Vii infinity at t. Ck of t is also an approximate equation. It's just written as an equal to because we are only calculating up to first order. It's minus Vki infinity e to the I omega ki by h cross omega ki plus another sum which depends on the rate at which Vki changes over time. So we are in a way distinguishing between terms which depend on the value of the perturbation at large positive times, the steady value it reaches, and a term which tells you how fast or how slow the perturbation change in between. Now let us put all of these together to find out the state of the system at time t. Let me just remind you of one thing. The coefficients in front of the energy eigengets phi I or phi n at time t are an of t and not exactly these cn of t's that we have found out here. The difference, of course, is that there is an extra energy dependent factor e to the minus I by h cross epsilon nt which connects the two. So we have to supply that extra factor along with the cn's in order that we can write down the state at time t, at least the first order approximation for the state at time t. So what we get is this. Psi of t is given by 1 minus I by h cross Vii infinity t, that of course is Ci of t, multiplied by e to the minus I by h cross epsilon it which converts the Ci of t to Ai of t, multiplying phi I, and for all the other states k which are not equal to I, you have the Ct that we had figured out, that's in the brackets here, multiplied by e to the minus I by h cross epsilon kt phi k. Now this expression certainly looks very complicated, but if you just manipulate it a bit, some patterns are going to emerge. The first thing that we are going to do is we are going to consider those terms in which the perturbation has reached its steady state value at t equal to infinity separately from the integral that we have left, which tells you about how the perturbation changes over time. So what we are doing here is that we are collecting together the terms which involve phi I, the initial state, in addition to contributions from all other states, but only those contributions which depend on the steady state value of the perturbation potential. Of course, in addition to that, you have an additional term which involves the rate at which the perturbation changes over time, and that is again a sum over all k which are not equal to I, which is there in the second line. We will next carry out a few manipulations which may look slightly confusing at first, but will make perfect sense to you once you realize that we are only calculating things correctly to the first order in the perturbation, so we can ignore all higher order terms. For example, right now what you can see is that the factor 1 minus I by h cross v I infinity times t is there only in front of the first term on the right hand side. What I am going to claim is that you can actually think of that as also multiplying the second term on the right hand side, the sum over k not equal to I that is there on the top line, simply because this additional multiplication by minus I by h cross v I infinity t would give rise to a second order correction to the wave function, and since we are only considering things to the first order in the perturbation, that extra term is going to make no difference. Remember, the term that you have in second place is already first order in the perturbation. Multiplying that by VII infinity is going to make that second order. So this is what we do. We imagine that 1 minus I by h cross VII infinity t multiplies both of the factors and take it out common. Now you should be able to recognize the thing that is sitting there in the brackets. Ket phi I is the unperturbed state that you started with. The additional piece that you have added, Vki infinity by epsilon I minus epsilon k times phi k, summed up over all k not equal to I, is nothing but the first order time independent perturbation theory correction term to the wave function. Note that at large positive times, which are the times we are looking at, the perturbation has already steadied out, so we can think about the perturbation now as a steady time independent perturbation whose value is given by V infinity. So basically this expression that you have in the brackets, ket phi I plus sum over k not equal to I Vki infinity by epsilon I minus epsilon k phi k, should be easily recognizable as the perturbed state according to time independent perturbation theory. This is what the state phi I becomes when you switch on the perturbation. Again, to first order in perturbation theory. Now the next step actually would also be in the same spirit of carrying out calculations to the first order in perturbation theory. The bracket which is sitting in the front, 1 minus I by h cross VII infinity t, can be replaced in this degree of approximation by an exponential of minus I by h cross VII infinity t. The reason is of course again simple. The deviation between the exponential and the thing that we had in the brackets is only second or higher order. But now you should realize that what this has done is that it has given me an e to the minus I by h cross t times energy correction phase factor, which you expect to have anyway, but that energy term is not epsilon I, but epsilon I plus VII infinity. But remember once again, what we are looking at is essentially a scenario where you have a steady perturbation, time independent perturbation now with magnitude V infinity. And VII infinity is exactly the first order energy correction to the eigenstate I because of the perturbation. So once again, what you should realize is what we are seeing here is essentially first order results from time independent perturbation theory. So it's rather gratifying that when we do a full time dependent calculation, at the end of the day, given the right circumstances, we actually recover results we have already figured out before from using time independent perturbation theory. So just by relabeling these things a bit, epsilon I plus VII infinity can be called epsilon bar I. So that's a perturbed energy eigenvalue for the ith state. That is perturbed, that is up to first order correct. And the ket in the bracket, ket phi I plus sum over k not equal to I and so on, that is nothing but the first order corrected energy eigenket. And so what we can do is write this whole thing much more simply in this form. It is a minus I by h cross epsilon bar it, where epsilon bar I is nothing but epsilon I plus VII infinity, the first order corrected energy, and phi bar I is of course the first order corrected ket. You may have noticed that we have also done something else here. We have replaced the epsilon k that you had in the last term by epsilon k bar. We have also replaced phi k by phi k bar. In case you are wondering whether that is a legitimate thing to do, let me remind you that this term already has a Vki, in fact a del Vki del t prime term here as a coefficient. So it's already first order in the perturbation. And so any difference between epsilon k and epsilon k bar and phi k and phi k bar would again be at most first order in the perturbation. So together, that and the coefficient in front would actually give us second order corrections, and we are ignoring second order corrections at this stage. But let me point out that this particular result has a rather nice interpretation. If you forget the rather messy sum for the time being, what you are getting is psi at time t is basically the perturbed energy eigenket phi I bar evolving with the energy epsilon I bar. But that is rather easy to understand. Once the perturbation has steadied out and a long time after it has steadied out, basically you are looking at a time independent perturbation with value, as I have said, V infinity. And the first term essentially is bearing that out. What time dependent perturbation theory is telling me is that if you use a perturbation to change the Hamiltonian from your original H0 to finally H0 plus V infinity, in the process of time evolution, the state behaves more or less like it is following the perturbed energy eigenstate as it keeps on changing with the changing values of the perturbation. However, there is also this additional messy piece which tells you that you can go out of the ith state. By the way, you have already gone out of the ith state as time evolves, simply because phi I bar is not phi I. But what we are seeing is, if you started with the ith state of the Hamiltonian, what was the Hamiltonian then? The first term essentially is telling you that there is a large probability that you are going to stick to the ith state, but now of the new Hamiltonian, the perturbed one. The term in the brackets, the sum over k not equal to I, is giving me the probability amplitude for the system to escape the ith eigenstate and go into another eigenstate. So if you use the fact that phi I bar, phi k bar in general, a general phi n bar is going to evolve with the perturbed energy epsilon n bar, and that is, it's going to pick up phase factors of e to the minus I by h cross epsilon n bar times t, we can write down psi of t in this form. Psi of t is basically phi I t bar, which is time evolved perturbed energy eigenstate, the ith energy eigenstate, plus a correction term which comes from the second term. Let us now take a look at what these terms actually mean. Firstly, it tells me that the probability of transition to the final kth energy eigenstate, not the initial kth energy eigenstate, this is the kth energy eigenstate of the final Hamiltonian, is given by pi to k of t. You just pick out that one term in the sum which talks about specifically phi kt, and the probability amplitude works out to be mod square of 1 by h cross omega ki times the integral that we have been looking at so far. Now, in the limit of very slow variations of v, this particular probability amplitude actually vanishes, simply because del v ki del t is too small. Basically, notice that if del v ki del t is very small and slowly varying, you can pull it out of the integral, and what you are left with in the integral is this rapid sinusoid to the I omega ki t prime integrated from large negative times to t, and as you should all know, such an integral essentially is damped by a factor of 1 by I omega ki. So basically what we are saying is, if 1 by h cross omega square ki times del v ki del t is very small in magnitude compared to 1, or as you can rewrite this in this form, del v ki del t, the rate at which the perturbation energy changes, divided by the energy difference h cross omega ki between the two states that we are talking about, between the state I, the initial state, and the state k where we are trying to go to. If this ratio is much less than omega ki, then you can essentially treat pi to k as 0, and so what we are going to have is this statement that under such a condition, the system is going to keep on following the ith energy eigenstate, not the ith energy eigenstate of the original Hamiltonian, but ith energy eigenstate of the perturbed Hamiltonian. And this is an example of a more general result in quantum mechanics which we have already explored in a discussion class, the Adiabatic Theorem. If the perturbation changes slowly enough, the system essentially stays in the instantaneous energy eigenstate that it started out with. Now, in the other limit, we can think of the impulse approximation, where the Vki suddenly jumps, or the perturbation suddenly jumps from 0 to its final value, V infinity, and this happens within a very short period of time. So, what we are assuming is del V ki del t, this rate at which the perturbation changes, is negligible outside a small window centered at some time t0. And then what will happen is, as far as this integral is concerned, though the integral is from minus infinity to t, it's essentially going to have contributions only from that small window, and in that small window, the sinusoidal factor e to the I omega ki t prime will not get to change much. The basic idea here is the time interval over which the perturbation changes in this impulse approximation must be small compared to 1 by omega ki, the typical time period of that particular oscillation that we are talking about. Now, if that happens, the result is actually very easy to figure out. The modulus square of e to the I omega ki t0 is of course 1, but more importantly, the integral that we have left now is something we can trivially calculate. It's nothing but Vki at time t, which is Vki at infinity, minus Vki at time minus infinity, which of course is 0. So putting that in, what we immediately get is that this particular probability of transition from I to k at time t is essentially given by Vki mod square by h cross square omega ki square. Now if you think about it a bit, this actually tells you that immediately after you carry out this impulse, the system stays essentially frozen in the original energy eigenkette. So this is my challenge to you, or this is a suggestion for a problem that you can work on. Try to interpret this result that we have obtained for pi to k at time t in the impulse approximation to the basic result that the state of the system does not change the moment the perturbation takes place. Immediately before and after the perturbation, the state of the system stays exactly the same, and it only changes after that under standard time evolution with the new Hamiltonian. The final example that we will deal with is perhaps the most important one of them all. This is the case of a periodic perturbation which starts at some time t0 and then keeps on going periodically forever. We will in particular talk about a sinusoidal time dependence for the simple reason that any other periodic time variation can be thought of as a sum of lots of sinusoidal terms. For simplicity, we will consider t0 to be 0. That's just something that makes the notation a bit simpler. And this is the perturbation that we start with. V of t was 0 for all negative times. That's what the theta of t is doing there. And then you multiply it by the actual operator, the operator f, which is a constant operator as far as time is concerned, multiplied by e to the minus I omega t, the sinusoidal time dependence. And to it you have to add its adjoint f dagger e to the I omega t in order to ensure that our perturbation is a Hermitian operator. Now the calculation of the time evolution of states due to this particular perturbation in first order perturbation theory follows simply from the formula that we have already derived before. All you have to do is carry out this integral minus I by h cross. You have to integrate now from 0 to t, because the perturbation vanishes before 0 anyway, the quantity v tilde ki. Here v tilde ki is simply vki times e to the I omega ki t, and vki, the matrix element of this particular operator, happens to be fki e to the minus I omega t plus f dagger ki e to the plus I omega t. And all we have used here is the fact that f dagger's kith element is a conjugate of f's ikth element. Now this integral is trivial to calculate given the fact that fki and f star ik are both constants, time independent quantities. So you can readily integrate this expression to get this form, and this can be further manipulated into a simpler expression by taking out e to the power half I by 2 omega ki minus omega t from the first numerator and a corresponding term from the second term as well. And if you do that, this ends up taking this particular form where the most prominent and important quantity is this function sine of omega ki minus omega by 2t by omega ki minus omega by 2 in the first term, and a corresponding thing with plus omega replacing minus omega in the second. Now a function of this kind should be very familiar to all of you. You have seen this in several places in physics. The single slit diffraction pattern, for example, comes to mind. And because we will need to deal with this function several times in the context of time-dependent perturbation theory for periodic perturbations, let us consider giving this a special name. So I will define square of this sine alpha t by 2 by alpha by 2 as a function of two variables d, t comma alpha. So with that, this expression simply becomes this. So the sine factors on both terms have been replaced by square root of d, t comma omega ki minus omega in the first term, and square root of dt comma omega ki plus omega in the second term. And I've taken the common factor to the I by 2 omega kit out of this bracket. So this is the final form for Ck. We need to explore what this form means, but before that, let me quickly give you a recap of what this function dt comma alpha that we introduced actually looks like. The form should be very familiar to all of you, and this is, as I said, a familiar pattern. You have seen this several times before. What I need to point out here is this. Almost all the non-zero contribution from this function comes essentially from a narrow region around alpha equal to 0. Here we have plotted the function at a fixed time t as a function of alpha. Near alpha equal to 0, you have a large contribution. In fact, at alpha equal to 0, this has a peak, and the peak is given by t square. The width of the function decreases with time, and you can estimate the width by just looking at where the position of the first minima on both sides, and it is easy to see that that width is given by 4 pi by t. So as time increases, this function becomes taller and taller, and essentially the region where you get contributions from becomes narrower and narrower. This should definitely remind you of a delta function, or at least something like a delta function, and that is going to be very important later on as far as long time behavior of a quantum system under periodic perturbation is concerned. As I have said, this particular form of the perturbation is very important and has a lot of interesting physics associated with it. Today what I am going to do is just give you a brief glance of the kind of applications you can have of this result. We will see the result in its full glory in later lectures. Now, to begin with, let me just point out one thing. The factors of dt comma alpha, which in particular are square root of dt comma omega ki minus omega in the first term and d of t comma omega ki plus omega in the second term, are very, very important here. And what you must remember is that this actually gives you a non-zero contribution only when the second argument is very close to 0. At least for large times, you get contributions essentially only from a very narrow range of alpha around t alpha equal to 0. Now, this of course is a probability amplitude C of k. To get the probability of a particle of a system in state I going over to a state k, where we are considering a discrete state k, is going to be given by the modulus square of this expression. And here all I have done is use the standard formula that z1 plus z2 mod square is z1 mod square plus z2 mod square plus twice the real part of z1 star z2. Let me point out that in this particular expression, the dominant contribution, at least for large times, is going to come from omega ki minus omega being very close to 0. That is, when omega ki is close to omega. So when your perturbing potential has a time dependence given by this frequency omega, which matches the energy gap. So when your perturbation has a frequency which matches the frequency gap due to the energy gap of the two levels, then and only then are you going to get a large contribution. This is what we call resonant contribution for obvious reasons. When you are considering an absorption of energy by the system, that is when epsilon k is bigger than epsilon I, so omega ki is positive, only the first term is going to contribute in a large amount. And so if you use omega very close to omega ki, in fact we are going to use omega exactly equal to omega ki to get a sense of what's going on. For omega equal to omega ki, what you have to do is use the fact that dt comma 0 is t square and ignore the contributions from the other terms, because d of t comma twice omega, which is the other term, is going to be pretty small. And so what you get is a probability which is given by fki mod square by h cross square t square. This, of course, is for absorption of energy by the system. If, on the other hand, the state K has a lower energy than the initial state, that is, energy is released by the system in the transition, then it is a second term which is going to contribute, and you are going to get Fik mod square by h cross square t square. What is important is that near resonance, the probability actually will grow quadratically with time. Of course, this cannot continue for a long time. This, after all, is a first order perturbation calculation. This will never make sense if the result that you get becomes too big. And as you can easily see, a probability which grows quadratically with time cannot give you the correct result if time becomes too big, because then it would tend to tell you the probability is actually becoming bigger than 1. This will of course break down unless t is less than a threshold time. Here we can estimate the threshold time to be h cross by mod fki, which is of course the time at which this formula for the probability will grow all the way up to 1. But you should realize that the first order perturbation calculation will actually break down even a lot before this, simply because once the contribution from perturbation becomes big enough, then first order calculation can no longer be trusted. You have to take into account higher order results. But at least as a good rule of the thumb, you can say at least for times which are large, so that but at least we can say that when t is much smaller than this threshold time capital TL, you are going to get this quadratic growth of the probability of transition to this other level. On the other hand, when we talk about non-resonant frequencies, let's say frequencies omega which are much bigger than omega ki, then we can use a quite different approximation. When omega is much bigger than omega ki, then omega ki minus omega and omega ki plus omega can be effectively treated as minus omega and plus omega respectively. And because d is an even function of the second argument, both the d factors in the expression for ck and pik are actually equal. If you just use that and use the fact that for rapidly enough oscillating things, as long as t is much bigger than omega inverse, the rapid oscillations can be averaged out, and using that average we will simply get pi to k as twice fki mod square coming from the first term plus fik mod square coming from the second term divided by h cross square omega square. The cross term in the probability contributes nothing because that term actually is rapidly oscillatory and averages out to 0. As a final example of the application of this particular formula for transitions to discrete levels, we will consider one which is not a periodic perturbation at all. Let us assume that we have a perturbation which was switched on at time t equal to 0. And this can be treated by the same formula simply because a constant function can also be treated like a periodic function whose period is infinite. That is, for this particular case, you have to take omega to be equal to 0. And once you take omega equal to 0, you can either use pi to k's formula or work directly with the ckT's formula. And it's easy to see that the probability ultimately works out to be this following expression: p times fki plus f star ik mod square by h cross square omega square ki times sine square omega ki t by 2. So here what happens is that as time goes by, you keep on getting oscillations. The probability of the particle landing up in the state k oscillates, grows to a maximum, then dips to 0 and then keeps on going back and forth between 0 and a maximum value. This kind of oscillation is very familiar in quantum mechanics, and we are going to see more concrete examples of this in specific models that we will consider in the next lecture. But let me point out the major application of this particular kind of perturbation is not in considering transitions to a discrete level, but rather in considering transitions to levels which are continuous. Either because, for example, you're talking of an atom which has become ionized and now the electron has a continuum of energy levels to go into, or simply because the energy gaps are too small for us to consider them as individual energy levels. It would be much easier to consider them as part of a continuum of levels. This is the kind of calculation that you will have to do if you want to understand absorption or emission of radiation by matter, which is one of the major applications of this kind of perturbation. We will deal with these things in some detail in a later lecture. Bye for now.